So let's continue from our previous video. And the idea of the previous video was to give meaning to numbers. So the conclusion of that video was that we have basically three different words: the real world, the conceptual world, and the mathematical world. And I'll just take one example from the last video, is that in the real world we see objects, actual objects, physical objects like apples. And in the conceptual world, we view these objects as a collection, or a group of, this is very important, abstract objects. We view this as a collection of abstract objects. We are not concerned with all the details. Abstract because we are only concerned in how many are there, as far as today's video is concerned. So, and actually the reason we need this is that we want to match these. So when I say abstract, I can think of a collection and I can call this the first and the second. You can come up with any other label. And then, it's not easy to write these labels. So in my mind, I have a store, a collection, another abstract collection of symbols. Let's say I use these symbols and I match these abstract objects. So in my mind, I am matching this first with that, if you want to have it that way. I'm actually matching this first with that, this second with that, and this first with this symbol, this first with this symbol. And then I say here that, okay, I declare this as two objects. Two objects. Here in this case, two apples. And we said that this description is needed because we need a type. So in general, because we are now restricting to counting complete objects, not half of an apple, not tenth of an apple, a complete apple. So instead of calling it a unit, it is typical to call it denomination. Denomination. Okay. And this is a concept which we call, this will be our number basically. So this represents a count. This is all from the previous video. You can also think of it as a as something measuring the size of this collection. How large is this? So this whole thing is an example of a quantity, one example of a quantity, which we will call multitude. So that it cannot be confused with another quantity which we have yet to study, and that is magnitude. So hold on. You can also call this numerosity. So we will use this multitude and numerosity to designate the full quantity. And the full quantity will have two parts. So if I now summarize everything, so in any case I will have my final mathematical description of this concept will be a new object which I will call multitude, a kind of quantity which comes out as a result of counting, and the first part of it will represent the count, and that will be our number. So this is my number, and this part will be the denomination, like apple, flower, and so on. That's how it goes. And similarly, I can complete this list. You must be wondering, last time I promised to actually dig deeper into this concept of number. Now we need to ask another question. So far, this concept of number, and one more thing, this is one way of looking at it. When you look at this as a multitude or a numerosity, you view this as kind of a size or a count of a collection. But here, look carefully, we are using this one too. Now this one is matching this first, and this two is matching the second. Here, this one and this two, they do not represent the size or how large, because we are not talking of collections. This is just labeling. So basically, we have two different interpretations of number. As a measure of size, largeness or smallness of a set, and as a labeling mechanism, like first. So you can see this as a shorthand for first, a shorthand for second, a shorthand for third. Now this is not to be confused with that, because these are two different things. Let me give you two more interesting examples. You are already using this, like your class roll number. Or registration number of a car. Registration number of a car. Now, a registration number of a car or your roll number doesn't mean that you are larger or smaller than your classmate, or your car is larger or more expensive. No, that is just a label. For the computer scientists, you can think of the address of a memory location, or the street address, street number. Now, street number doesn't mean that street number 100 will be larger or longer than street number, for example, 50. No, that's not what is meant. So two different meanings. Say it with me. Size of a collection, and as in labeling. You can also call it indexing. So this interpretation is the indexing interpretation. So the question I need to ask now is, do these numbers exist independent of the physical examples? So imagine we humans were not there, and there was nobody to experience apples and flowers and pen, and there was nobody in this universe. I mean, the number concept is so abstract that you must be able to imagine it or define it independent of the physical reality. So, if we can do that, then we will get convinced that numbers have a universal existence in this universe. So, imagine I now have a collection of objects, and those objects don't exist, they are just concepts, they are not physical objects. So let's start with nothing. So the concept of nothing, I have a concept of nothing, I'm using the same. In the real world I have nothing. Now this nothing is basically, let's use this shorthand. An empty set is a very good representation of nothing, and I can use the shorthand. This phi can represent nothing. So in the math, I can now think about the size of this set, because there are no elements. So that count or size, I can use a symbol 0 to represent the number of objects in this empty collection. Perfect. Makes sense. It's just a symbol. Similarly, I can now come up with another collection. I will build a connection out of nothing. I'll put this as a member in that collection. Now I have a collection of one object, but that object is not physical. It is just an abstract concept. But it is still different. This collection is different than that collection. That collection has no member. This collection has one member. Even if it is abstract, it is one member. So now I can say that I have one member. So here I can write the count or the size. Yeah. Similarly, I can have another collection where I have this as my first member and this as my second member. Now I have an abstract collection with two abstract concepts instead of one, two, and so on. Let me just complete it so that in case you are curious. Pick this one, then pick this one, and next pick this one. Yeah, so it means that I can construct all these natural numbers out of nothing. So, which establishes that these numbers exist regardless of my existence, regardless of your existence. Stay with me. So I think we don't have time left for this video. I want to keep all these videos to within 15 minutes. So let me give you a recap of the next, or maybe I can tell you something about how your mind processes these symbols. So you can now think of a set of natural numbers or whole numbers, yeah, including this 0. So you must imagine that in your mind you have a machine. Let me just represent that machine, because some of you may find this construction very difficult to understand. So let me find another construction. Let's say you have a machine inside your brain which gives you the next number in that collection of numbers. So now I have a set of natural numbers, and I need to know how my mind generates all these different numbers. So the first number is 0. Yeah, this is the starting point, and now my internal, some part of my brain is able to start with this 0, and it will generate the next number. Let's give it a symbol, because now this is not important what symbol you use. What is important is that you are able to conceive a different number, and we will call it the next of 0. That same logic, that same part of the brain is able to process this one and give you the next symbol, 2, regardless of how you represent this 2, what base or what symbol, and so on. Yeah. So now this will never stop. You can imagine any number. Let's write this hash for the number, and you will always have a next of this. You will have to invent a new symbol. So these numbers will never stop. That's what we mean by an infinite set. Infinite doesn't mean that you have a largest number, but it simply means that at every stage in this counting process, your mind can generate the next number. That's what we mean by the set of natural numbers, which by its very definition, by this definition, that for each number, a next number will exist. Yeah, it doesn't matter what you call that, how you write it, how many decimal places, no, it doesn't matter. The fact that this will never stop is what we mean by infinity. So, in the next video, I'll give a physical meaning to addition, what we mean by addition. So, wait for the next video. Thank you.